Hi, guys. Yeah, I guess we can get started. So my name's Adam. I'm a flight software engineer at Lynk Global. I've been working with them for about a year and a half now on our flight software platform. And we're going to be talking about software updates today. So if you've never heard about Lynk before, we kind of fly under the radar. We're a company building direct-to-device satellites. So essentially, your cell phone can connect directly to the satellite and get text messaging data, normal cell phone communications, all that kind of stuff. We build what we call kind of pizza box shaped satellites. So they're, you can see two of them there stacked for flight. And we build all of our satellites in-house, and we have a big focus on kind of, doing things ourselves, doing a lot of rapid iteration and, trying things out, learning and moving quickly on that. And so, I mentioned this morning a lot of the great things about iteration and moving quickly. One of the things that can make this difficult is software updates. So, if you're iterating really fast and you're always trying new things, you're constantly updating the software on your satellites. So right now we have 5 satellites in orbit. We want to put up like 5,000, I think. And we currently do an update about once a week. So actually, I checked on our schedule this morning. This morning, we've done 2 updates. We're going to do 2 more this afternoon, just today. And that's fairly typical. And so the process that we had before was very manual. For each satellite, you have to kind of take the update bundle, you have to put it on each spacecraft, you have to command it and validate it. It takes a few days to fully deploy one update to the entire fleet. If you do this for 5,000 satellites, it's going to take you years to just put up one update on the spacecraft, and that's obviously not going to work. So we wanted to develop a system that would allow us to essentially put our updates on the spacecraft, to do it deployment fleet-wide, and do it in a way that was scalable, autonomous, and reliable. We do updates for a lot of different things. I think maybe about 70% of the updates that we do right now is to kind of add a lot of autonomous features to the spacecrafts so that they can work by themselves a lot. There are also bug fixes, adding some features. Sometimes you'll launch with some features disabled, and you kind of enable those later on. That's the kind of stuff that we're deploying. So a few requirements that we kind of wanted to lay out for the system. We wanted it to be able to kind of automatically build and prepare those updates before they get sent to the spacecraft. We wanted to be able to store those on the ground and kind of, have a log of what updates we actually deployed. We wanted to be able to not just deploy the updates to the entire fleet, but also to be able to deploy it to a subset of the fleet for doing like canary releases, or even just deploying it to a single satellite if you want to test something out. We wanted to be able to deploy or choose the deployment times based off of a rule-based system or a schedule. We wanted to be able to track the deployment status across the entire fleet. So we wanted to know for each satellite what updates had been applied, when had they been applied, did they work, did they not work, all that kind of good stuff. And we wanted to be able to do these updates safely. So if they don't work, we want to make sure that it rolls the system back and puts your spacecraft in a good known state and doesn't do any damage. So I've kind of laid out what I think are kind of the 3 good pillars of a good update system. First part is a pipeline that kind of builds and prepares those updates on the ground. The second part is a system that takes those updates and actually puts them on your satellites and chooses a time to execute the update. And then the final part is a system that can actually perform the update and make sure it works. And if it doesn't work, roll it back and put the spacecraft in a good state. So talking about the first part here, this is kind of a diagram that we kind of outlined of what we think a good process could look like for building and preparing those updates. So this is something you kind of run every time that you want to release a new piece of software on the spacecraft. First thing that an engineer would do is they tag the release and it will trigger a CI pipeline that builds and bundles the update and deploys it to our flatsats. We have, 1 flatsat per kind of hardware generation of spacecraft, and you want to deploy it to all the ones that are actually going to get used here. For each of these flatsats, the bundle gets deployed, and then you kind of run a suite of automated integration tests what those integration tests are going to do is you want to kind of test any of the new features that you're introducing or any of the bugs that you're fixing, make sure that they're actually fixed. You want to test for any regressions, make sure you haven't introduced anything new. You also want to kind of just run the spacecraft through some of its normal paces and normal operations and make sure that just, you haven't missed anything and that everything works fine. That should kind of be done all automatically through a testing framework. The results get all uploaded and consolidated, and then the idea is that you present the operators and the engineers with a kind of a test report saying, here are all the tests that ran, did they work, did they not work, and from there you can review and decide if you decide if this is an update that you want to deploy or if you want to do more work. And this is all well and good. This works really well. One of the issues that we have with this, though, is that this works well for releases, but the flat sets that we have are a pretty precious commodity. There's a lot of engineers that all want to use the flat sets. They all want to test things out, and so it can sometimes be difficult to find time, especially for release testing, where there can be a lot of tests that you want to run. And so this works for releases, but if you're doing feature development, it's hard to find time on the flat set. So we kind of have a bit of a different process that we're laying out for that, where we utilize a lot of a software simulator a lot. And the software simulator is basically running the exact same flight software that we're running on the flat set, except we just virtualize all the hardware interfaces and simulate those. And once you do that, then you kind of have a setup that is, you can basically duplicate as many times as you want, as long as you have the server space and the compute for it. And yeah, so you end up kind of being able to set up a system like this, where you can have a software simulator that's just for development. And so each developer can kind of have their own software simulator for experimentation. And then you can also create a bit of like a CI workflow, where every time you want to merge a feature, it can run a process where essentially it'll build the update, deploy it to a software simulator, and run the tests and kind of approve or reject your changes that way. And software simulators aren't quite as good as the real hardware. By abstracting away some of those interfaces, you can create problems or things that you might not catch. But kind of the nice thing about this system is that all your tests that you're running here as part of your feature development are going to get run again as part of the release testing. So, you're not really, if there are any issues there, you'll catch them at release testing. The idea here is that you're kind of just catching them earlier. If there's an issue, you'll find it, you can fix it, and that way they're not making it all the way to the release testing, and hopefully it makes your release testing run a bit smoother. So that's kind of the first part of that system. So preparing the updates and bundling them up. Second part is kind of getting them on the actual satellite itself. And this is not a very unique problem to satellites. We kind of identifies a lot of parallels to IoT devices, where if you're an IoT device manufacturer, you're going to have a bunch of devices out in the field. They all need to be updated regularly, and you need a process to do that. And so there are IoT solutions out there that exist that are just for this, for storing and deploying updates to a fleet of IoT devices. And we kind of looked at, did we just want to use one of those solutions for the satellites? And we ended up not. We ended up kind of rolling our own solution. And it's partially because there's a few considerations for satellites that make them a little bit unique. One of them is that you don't necessarily have an internet link. You can have different communications protocols and different setups there that these solutions don't necessarily support. We wanted to have a lot more control over when the updates get deployed. I don't know if you guys have ever used like a smart toaster or something like that, and you want to go make your toast, and it has to update before you can actually make your toast. We can't have that with a satellite. We need to have really good control over when we actually deploy those updates. We also have, constrained bandwidth, limited connectivity. These issues, they're not necessarily unique to satellites, but they made our use case not really work well with the existing solutions. So we ended up rolling our own solution here. And there's two parts to this. There's a ground software side and a flight software side. And the ground software side is really important and really cool, but I won't talk about it too much because this is a flight software conference. And it's a whole thing in and of itself. But the flight software side of this is something that we call the flight update service. And it's a system that runs on every satellite on orbit. It's a persistent service that's always running, and it's tracking our updates. So it has a database that tracks past, present, and future updates. It handles the actual execution of the updates themselves. It supports the rollbacks, so that if the update doesn't work, it can put it back in a safe spot. And it's written in Rust. And I'll talk a little bit about why we use Rust here. We use Rust actually a lot in the flight software on our spacecraft. We also use it in the ground systems as well. We transitioned to it a few years back, and some of the reasons why we really like it, it has this, if you guys have used Rust, I'm sure you know all this kind of stuff already, but it has this really great borrowing and ownership model that's allowed us to do a lot of asynchronous stuff on the spacecraft and not really worry about kind of some of the typical gotchas that you have with asynchronous programming. The air handling the air handling in the language is really awesome. It makes you really think about how you want to handle your errors, and makes you kind of like lay out really good exception handling workflows and stuff like that. It has a really great type system and a lot of compile time checking. So when you actually go to deploy our code and test it in the field, we're pretty confident that a lot of things are going to work, and there's a lot of things that it catches early on, which is really awesome. It has a really awesome ecosystem of libraries. So there's a lot of library code that we use. There's a lot of crates that are actively developed and maintained, which is really awesome. So there's constantly new stuff happening that we can integrate and test out. Also, their environment management and like their package management for Rust is great. So it makes it really easy to kind of incorporate this into your code. And then finally, it's really easy to cross-compile your Rust code, which is really awesome. Typically cross-compilation is just a horrible part of your process, and this makes it really easy. It also kind of statically links our binaries. So when we're actually deploying the Rust code, we don't have to really worry about all the dependency management. It's just one file that goes in the spacecraft, and we know that it's just going to work. So kind of just laying out what the structure looks like. It's a very simple program with 3 layers. You have an API layer that communicates with the other systems on the spacecraft and with the operators on the ground. You have a logic layer, which is the actual business logic of the system that handles executing the updates. You have a persistence layer, which is tracking the tracking the updates, tracking their status, and all the details about it. And the way that this gets used in our system, so first of all, before you even go to actually execute the update, there's a registration step. And how this works is the ground system will put the update bundles on the spacecraft and call a command that registers the update with the update service. And what it's going to do then, it's going to look at that update bundle. It's going to grab a bunch of metadata from that update bundle and track it so that it knows all the information it needs to know about that update. And then you can go and command it. And there's 2 ways that you can command the update. The first is a direct update, or the other one is a queued update. Direct is basically as soon as you send the command, as soon as it receives the command, it's going to start executing that update on the spacecraft. Queued is basically, puts all the updates in a queue, and then you can start the queue processing, and it will just basically start knocking out those updates one after another. Or you can also stop the queue, and it will stop processing the updates that are in that queue. And when you kind of use this with a ground-based scheduler, this is kind of what gives us our control over when you want to actually deploy the update. You can use, with that ground-based scheduler, you can essentially look at the activities for the spacecraft, figure out when is it providing commercial service to the customers, when is it, not doing that, for example, if it's over the ocean, and you can start scheduling update executions for those time periods. You can use the direct update for updates that are very time sensitive. If you need it to happen before a certain time or whatever, you can do it there. Or if you have updates that are less critical that just need to be done at some point, you can put them in the queue and then it will process them when it has time. So when you go to actually execute the update, this is kind of the flow that it goes through in the system. First of all, this assumes that the update's already been registered. The operator or the scheduler will send the command to actually perform the update. That command gets passed to the logic layer, which will extract all the information it needs from the database to perform it. It kind of puts the system into like an in-progress state, which basically stops it from being able to perform other updates at the same time and avoids doing that in parallel. It will actually command the update to install, receive the result back if it's succeeded or failed. It'll put that information back in the database along with logs and all that kind of stuff. And then it sets the system state back to idle to process the next update. One of the things you'll notice here that's a little bit weird is you'll see that we're putting the system state in the database itself. The reason why we do this is it allows us to do self-updates. So essentially, the update service here can update itself. And how it does this is by basically loading itself into memory. starting to perform the update, putting the new binaries in place. It's going to write the status of the update into the database, and then it's going to restart itself. Once it comes back up, it will read that it's currently it will read that database, see that it was in the middle of an update. It will finish the update and be complete. This also kind of allows us, by having that same setup, it allows us to potentially resume an update if the system crashes, as it can kind of come back up, see it was in the middle of an update, and finish it. Now, the last part of the system, you can see on the right side here, we're just commanding the update to install and receiving the result. So what's happening over there? That kind of looks like this. And there's basically a workflow that we have here for deploying the update that follows this state diagram here. The first step is the copying step. So an important thing to mention here is this flight update service is only really running on the main flight computer of the spacecraft. And there's a bunch of other computers on the spacecraft doing a bunch of different things. So the first step is, if this update is going on a computer that isn't the main flight computer, you got to copy the files over, power that computer up, make sure it's ready to be updated. Second step is the backup stage. So basically, that update bundle that you're installing has instructions on how to actually install that update, what files go where. And so it's going to look and see, are these updates, or are these files overwriting any files that currently exist? Is there going to be any issues there? And if they are overwriting any files, they're going to back those up into a backup folder. From there, it's going to install the update. So following the instructions, putting the new files in their new locations. It's going to validate it, make sure that the update was successful, and then if it's done, if it was successful, it'll just return success. And you can see we have this, like, the red arrows there, which is basically, if anything goes wrong during any of these steps, what do we do? And if something goes wrong during the copy stage or the backup phase, you're fine. You just say that the update failed, you can try again next time, no harm. If you get as far as the install, where you're actually starting to modify the files, or the validation phase where it's already modified, you need to put the system back into a good state. And that's what this rollback phase does. Rollback phase basically just goes and unrolls everything that it did. So any new files that were installed, it's going to delete them. Any files that it backed up, it's going to put back. There's also kind of a spot for running like custom shell scripts. So you can kind of like, if there's any custom logic that you need to do, like modifying databases, that kind of stuff, you can run it there. And that, in theory, puts the system back into a known state. And then at that point, you basically just mark it as a failure. The operators on the ground will see that, and they can decide, based off of the logs, what they want to do next for that update. And now, you notice it says there's a validation step here. So what is that actually doing? Well, the validation step is kind of an optional step that we allow for our programs to figure out how they want to it's an optional step that we provide that allows these programs to validate themselves and make sure that they actually worked. And it's implemented as a bit of a self-test feature. So essentially how this works is, when the update service executes the update, it's going to pass a validation key to the program that's being installed. And it's then going to set up a server over an IP connection, and basically is just looking to receive that validation key back before a timeout occurs. If the timeout occurs before it receives the key, it's going to roll back the update. If it gets the key, it's going to mark it as a success, and the update is done. And the update service really doesn't care how it gets that key, as long as it gets it. So it's entirely up to the program that's being installed to decide how they want to perform that validation. It can be something as simple as, did the program that got updated, did it basically just initialize, and did it come up, and then at that point it can send the key? It can perform some basic tests to make sure that it's functional, that it's doing what you expect it to. It can perform hours worth of testing and kind of run through the full suite of things that it's expected to do and make sure that it works properly. And that's an option that you can do as well. You can even make it so that the program itself isn't sending that key. For example, if you're updating the communication systems on the spacecraft, you can make it so that that key has to come from an operator on the ground. So, the update is performed, you have to review telemetry on the ground, and then an operator can then, from the ground, command the spacecraft with that key for the update to be applied, and that way you ensure that post-update you can still contact the vehicle. The timeout for that system is entirely defined by the operator and the person making that update. So you can set that timeout to be, a minute, 10 minutes, an hour, or even days, if you have something that you're really worried about. So kind of bringing that all together, so there's 3 pillars to a good system. So first part here is preparing that pipeline and updates. which is preparing the bundle, running the flat sat testing. Second part is getting it on the spacecraft. So that's uplinking the files, registering it, and then finding a time through that scheduler to command the update. And then the final part is the safe deployment of that update, which is performing that update, going through that state flow diagram, and either rolling back the update if it didn't work or marking it as a success. So where we're at with this, we have about 80% of this actually deployed in the field. We're kind of currently in the process of testing this out, figuring out what works and what doesn't work. We're only doing it with our fleet of operational spacecraft, so we don't really know for sure if this is going to work for 5,000 spacecraft or not. But the idea is that we think this is allowing us to have a lot of automation, and a lot of the parts that will scale with the number of spacecraft shouldn't really scale the amount of human effort involved. And the reliability features that are introduced by kind of having that rollback workflow and making sure you put the system in a good state ensures that even with that many spacecraft, that you can do these updates with confidence and know that you're not going to do damage. So this is something that we're trying out, and we're going to see if it works or not. And yeah, I can take any questions.
Thank you very much, Adam. We do have time for a couple of questions, so we'll take one in the room, and then we'll go to one on Slack and come back.
Since I have the microphone. Are those updates you're talking about, are these patches or the core images?
Sorry?
The updates you're referring to, are they small patches, or are you entirely updating the core image?
So right now, almost all the updates we do are patches. That's something that we're actually working on, is like being able to do, can you do full operating system updates? That can get a bit more challenging because like the file size constraints. And so you want to look at things like that, of like seeing if you can do like delta updates where you're just updating, the parts that have changed and stuff like that. And there are systems that allow you to do that. But right now, pretty much everything we're doing is kind of just software patches on top of the existing OS.
Can I have one? I know this is a software workshop, but I'm going to bring some more bit of mechanics in it. You have LEO satellites, right? 10 minutes.
Correct.
Overpass over the ground station, more or less. How do you manage the time? Let me rephrase the question. What happens to the spacecraft during the update? Do you go in idle mode? Do you still have operations? Pretty much following his question. Mission downtime. My advice, if you scale to 5, can you scale to 5,000 and figure out any software update or any single spacecraft or multiple, how much downtime or uptime does that leave to the constellation? Over?
Yeah, that's a great question. So depending on the update, there may or may not be downtime. It doesn't necessarily have to reboot all the computers. So if it's not an update to the core systems that are providing commercial functionality, it doesn't necessarily cause downtime, but it could cause downtime. I think one of the great things about the Earth is that it's mostly water, and so we don't provide service over water. And so this kind of guarantees that like it doesn't really matter how many people are using our service and like that. There's always going to be times when the commercial service is not needed, and that's kind of what you can interface with the ground scheduler and find those opportunities that you can perform the updates. I think that works for most cases. There's a few edge cases for that, but that's kind of the idea.
All right, let's take a question from Slack here from Hyung Sub Kim. The question is, I wonder how you test or verify the correctness of the patch code. Do you use manually created test cases or any automated tools such as fuzzing or formal method?
Yeah. The automated testing part is kind of the least developed part of our system at this point, I think. We have a lot of the other automations in place, but the actual automated testing is pretty basic at this point. So I think short answer is like, no, we don't have any automated tools that we do for test generation at this point. It's pretty much all manual. That's something that's going to have to change. And I think we'll have to incorporate a lot of automated test tools in the future.
All right, and I will take one more from Slack because I skipped it by accident. So from Vikash, how do you ensure real-time reliability and rollback safety when deploying large-scale software updates across thousands of satellites with constrained bandwidth and intermittent connectivity?
How do we do real-time?
Yeah, how do you ensure real-time reliability and rollback safety?
So I mean, like we use the, the workflow that we described for installing the updates to do our rollback setup and using the validation methods to kind of ensure that it works correctly. We don't have a lot of real-time constraints for what we're doing. And so it's really just about like, once the update's been performed, doing the checks, rolling it back if it works. And if there's a bit of downtime there, that's fine. So yeah, I'm sorry, I'm not quite sure I'm understanding the question perfectly, but I hope that's helpful.
I think